All right, believe it or not, we're entering the last part of chemistry, and this is perhaps the most practical part of chemistry. You're going to learn a lot of stuff that's just going to make life make a whole lot more sense. So, let's begin by talking about this guy climbing on an iceberg, which is kind of crazy. Notice he's got a horn, right? That looks like a shofar, a ram's horn, except that it's metal. It's not a horn?
It's a climbing thing.
Yeah, it is a climbing pick. All right, so this is, of course, an extreme sport. You probably don't want to be stepped on your toe by this guy either. That could be kind of painful. Now, for you guys, this is no big deal. You've seen icebergs, you've seen ice climbers, you know, but you do realize that this is really, really bizarre when it comes to chemistry. The fact that this guy is climbing on ice is really, really strange. You see, the fact is that the Earth is 70% water. So the chemical that we are most familiar with is water. We are 60% water. Nope, the Earth is 70%, we are 60%. And so the chemical that we are most familiar with is water, and yet water is one of the most weirdest chemicals in the universe. Okay? Water solid floats on its liquid. Guess how many other chemicals can do that?
Zero.
None that I know of. It's chemistry, so I wouldn't put it past something somewhere, some rare chemical that it can do that. But water is the only one that I can think of whose solid is less dense than its liquid. This is strange. Any other chemical, this board would go straight down to the bottom of the sea with the sailor along with him. Actually, any other chemical, if I was to kind of push you over the side and you would land into the liquid, into the deep side of a pool that's filled with that liquid, it is very likely that you wouldn't be able to swim back up in order to survive.
You just fall straight down.
You would go straight down and you would try to swim, but you wouldn't be able to. Why? Because think about what you do when you swim. You grab a hold of water and you push it behind you. Why can you grab a hold of water? Yes?
Because your body's made of mostly water.
No. Surface tension. Cohesiveness. The fact that water will stick to itself allows you to grab a hold of it and push it down. Okay? That's what allows you to swim. Well, what if you're swimming in a liquid that has very little cohesiveness? Well, then your hand would slide right through the liquid, not being able to allow it to propel you back upward. So you would drown in the liquid because, not because you can't swim, you might be the greatest swimmer in all the world.
Because you don't have enough surface tension to push yourself back.
Exactly. You don't have enough surface tension to pull yourself back up. All right, or push yourself back up. So what allows you to actually surf? Surface tension. Okay? This is really, really bizarre. Only water can do this. And if it wasn't for water being able to do this, life could not exist here on Earth. Water as a gas is 2,000 times less dense than water as a liquid. That makes sense. We can understand that one because, you know, gas molecules are really far apart. And yet, water and ice are very close together in density. That's really strange. And the fact that water, usually it's somewhere liquid and solid is somewhere in between the gas and solid. I mean, the liquid is somewhere between gas and solid in its density. The fact that in water the liquid is above, slightly above the solid, is very, very strange. It takes almost 7 times more energy to convert liquid water into gaseous water as it does to convert solid water into liquid water. Why? We'll find out. Check out the density. Not much different, but enough. But the reason why it's that much, not much different, is the reason why the Titanic sunk. Why? The iceberg was able to float. They could see the iceberg from a distance.
Why couldn't they
Yes.
the whole iceberg wasn't above the water?
Exactly. If the density of the solid water was much lower than that of the liquid water, then they would have been able to see most of the iceberg above the water. By the fact that they are so close means that they could only see about 10% of the iceberg. And what did they plow into? The 90% that was
Not.
underneath. Yes, sir.
Why? I'm really confused about it. Why couldn't they turn the Titanic away from the
Okay, big, giant. I mean, at the time, it was the biggest ship on Earth.
It looked fairly small.
So the bigger the ship, the harder it is to turn. Water and ice are more alike than steam. Why? How much of the Earth's surface is covered with water? 70%. Why is water so important? How much of us? 60%. Live near an ocean or a large lake? What are you going to find? You don't have many extremes in temperature. That's why Seattle doesn't rain much. It definitely rains a lot. Doesn't snow much in Seattle. Rains a lot in San Francisco, doesn't snow much. Definitely doesn't snow much in LA. Any city near the ocean is not going to experience a lot of snow. Okay? Get inland and you do. Why? Because water is going to moderate. Water is going to prevent the air temperature from getting too cold or too hot. Yes, sir.
So apparently a 12% deficiency of water leads to that.
Yeah. And you can have actually too much water in your body. Your auto engines, of course, is cooled down by water or something mixed with water. Nuclear reactors are cooled down. That's a high specific heat, right? How about this one? You've studied world history. Why is it that all the ancient major cities were either on a river or on the sea? Why was transportation so important? Elaine? Trading. Okay, if you live in a large city, you're not self-sufficient. If you live in a small village surrounded by agriculture, you may be self-sufficient. You may be able to grow your own food or hunt for your own food. But if you live in a city, you're not self-sufficient, which means they are dependent on what, Elaine? Trading. And at that time, in ancient times, before trains and planes and automobiles, okay, what was the fastest way of moving from one place to the other? Boats. Okay, so look on worksheet 12.1. There are 9 properties of water that I need you to be very familiar with. It says 8, but I want 9. This video will take you through the 9. Ready?
Imagine an Earth without water, life without water. We find it everywhere, in the atmosphere and below our feet. 3/4 of the Earth's surface is covered by this essential liquid. It's a difficult thing to imagine life without water, because our own survival depends on it. In fact, water is vital to the existence of all forms of life on Earth. Water, or H2O, is an unusual compound with amazing properties. These unique properties are what make it so important to life. First of all, water happens to be the only substance on Earth that can be found naturally in all three states, as a solid, a liquid, and a gas.
If the temperatures are low enough, and I'm talking about, in Fahrenheit degrees, 40 degrees, you can look over our rivers, and actually it would have to be close to 32 degrees. You could look over the rivers and see maybe some ice sitting on top of the water. That's solid. You could see water that's liquid, and in the early morning you might actually be able to see mist coming off. That is evidence of gas. Do you realize how strange it is to be able to see all three phases of matter at the same time? That's what they're doing over there. They're getting some carbon dioxide, solid, dry ice, and putting in a pipette and letting the pressure build up in order to be able to see all three phases of matter. Okay? And if they're not careful, the thing blows up in their faces and it showers them with water. We don't talk about that.
Imagine an Earth without water, life without water. We find it everywhere, in the atmosphere and below our feet. 3/4 of the Earth's surface is covered by this essential liquid. It's a difficult thing to imagine life without water, because our own survival depends on it. In fact, water is vital to the existence of all forms of life on Earth. Water, or H2O, is an unusual compound with amazing properties. These unique properties are what make it so important to life. First of all, water happens to be the only substance on Earth that can be found naturally in all three states, as a solid, a liquid, and a gas. It is rare in that it actually expands.
It is less dense as a solid than it is as a liquid.
As a solid, which is why ice can float. Pure water is essentially colorless, odorless, and tasteless. Water has a neutral pH, which means it is neither acidic nor basic. Water has been called the universal solvent because it can dissolve many substances. Wherever water goes, either through the atmosphere, the earth, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This is one reason why water accounts for about 70% of the weight of a cell, which is the building block of life. Water has high specific heat, which means it absorbs a lot of heat before it changes temperature. This is why water makes a great coolant. This is also why oceans, lakes, and water vapor in the atmosphere help to regulate the Earth's temperature.
Okay, so you got high specific heat, right? What about colorless, odorless, and tasteless?
Water molecules are sticky. They attract to each other, which is why water tends to float together, fall as raindrops, and bead up on the surface of a leaf. This property is the result of cohesion. To understand cohesion, let's imagine we're recreating a water molecule. A water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. Because of the molecule's arrangement and the electronegativity difference between the hydrogen atoms and the oxygen atom, the molecule becomes polar. The oxygen atom has a negative charge, while the hydrogen atoms have a positive charge. Since we all know opposites attract, the oxygen atom will stick to a nearby hydrogen atom. The result is a strong bond. Surface tension is a result of
High surface tension.
cohesion and is the measure of how difficult it is to break the surface of a liquid. We can observe the high surface tension of water by watching this mosquito step onto its surface, or this insect as it struggles to free itself from a droplet. Surface tension is also what causes a water droplet to take a spherical shape. Water is the most cohesive of all non-metallic liquids. Adhesion is similar to cohesion, but refers to
So adhesion has to do with water sticking to itself. Cohesion is water sticking to itself. Adhesion is water sticking to other things.
two different surfaces or molecules with an attraction to one another. This is why the droplet sticks to this leaf. Along with cohesion, adhesion is responsible for a phenomenon called capillary action. Capillary action is the force that pulls water upward against gravity through a narrow tube. This is an essential property for plants, which rely on capillary action to pull water from their roots up to their leaves. So it's pretty obvious that water is important stuff. Humans rely on it for personal consumption, as well as things like industry, energy production.
All right. So you got them? High specific heat, capillary action, cohesiveness, adhesiveness, neutral pH, universal solvent, less dense than its liquid,
found naturally on the base bond.
Yes.
Found naturally in all three states.
Found naturally in all three states. Yes. All right.
The ice bomb
Watch this
illustrates the
video.
fact that the volume of ice is greater than the volume of an equal
So you
mass
have
of
something
liquid
that looks
water.
like a hand grenade.
Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed.
No, I don't think I've ever. I have shown you this. Okay. So notice that it is so full that the water will actually squirt out. So there's no room at all. It's just water in there, no air.
The bomb is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath. It takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield. Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides.
All right, I can explain the concepts of normal freezing point and normal boiling point microscopically and macroscopically. Here we go. So what happens when you heat ice? No. Molecules gain enough energy to break the weak bonds that hold them rigidly together, and they start sliding past each other. That's right. Now, if it happens at standard pressure, which is the pressure at sea level, we say that it is normal melting point. Back when you were in middle school, if I had asked you what is the melting point of water, there is a chance that maybe you would say 0 degrees Celsius. After this chapter, if I ask you what is the boiling point of water, or the melting point of water, you would have to look at me and say, what pressure, Mr. Moreno? because you will now know that the air pressure can actually affect the boiling point temperature and the freezing point temperature. What do we call the temperature at 1 atmosphere when liquid turns rapidly into gas? Normal. So I want you to associate that word normal with meaning that it's happening at a standard condition. In our case, sea level. What do we call a graph that illustrates these temperature changes? It's called a heating curve. A heating curve. Okay, so I'm going to explain to you this heating curve, all right, using an analogy. Behold, Elaine. Okay, so in a few minutes here, Elaine's going to raise her voice. First of all, Elaine's going to now get up and get the bag and put her remote in the bag and pass the bag around. After she does that, she raises her hand and says, Mr. Marino, I need to go to the potty. Okay? So I say to her, well, not unless you give me $1, you're not going to the potty, which I realize is probably somewhat illegal, but this is my analogy and it doesn't have to be legal. All right? So Elaine looks at me with that pitiful look that she has sometimes and says, but Mr. Marino, I don't have $1. So not only do I give her $1 because I'm just the kind of teacher that I am, but I give her $19. And I say, I just need $1, Elaine. So Elaine looks at me, hands me $1, pockets the 18, and starts to get up. So get up, Elaine. Please. Get up. Please, get up. Okay, she gets up and starts to move toward the door. Stop. At this point, you feel a tug around your waist, and you look down and you realize there's a thick rope around your waist. And that rope is attached to Robert, who is now leaning toward you, looking at you sheepishly. Okay? You move now a little more forcefully over, and Robert plops on the ground. He is now sprawled on the ground. And you realize that there is a problem. Okay? Not only are you hooked to Robert, Robert is hooked to Ryan. Ryan is now tied to Danielle. You are all tied together. So you're going to have to go to the restroom. They do not have my permission to go to the restroom, so they are going to have to be dragged by you all the way to the restroom. So have a seat. We've got a situation here. All right? So the situation is this. You have $18 in your pocket and a need to go to the restroom. You have my permission to go to the restroom. Unfortunately, they do not have my permission to go to the restroom because they have not given me $1. And I have now given you all my money. So, what would you like to do about this? Hold it till next period? Hold it? You can't. I mean, you're feeling the need to go. Keep in mind, there's 18 buddies of yours that you're interconnected with. There's $18 in your pocket. Okay? This is where chemistry drifts a little bit into political science. You would like to be capitalistic and you would like to keep the money and hopefully invest it and make more money, right? So you can buy more stuff. I don't blame you for wanting to hold on to the money. unfortunately, because you're interconnected to all of these guys, then we're going to have to consider the Three Musketeers scenarios in this situation. All for one. So if you want to go potty, guess what you're going to have to become? Not a capitalist, but a socialist. Spread the wealth. So she takes out from her pocket the $18 and she gives all 18 to Robert, who takes one and gives 17 to Ryan. Ryan takes one, gives it to me, and then pockets the rest, and we all look at Ryan. We go, Ryan, socialism works in this instance. Okay? Yes, it does, because if you need to go to the potty, you're connected to everyone. All for one and one for all. So finally, the money gets to Sierra, and she's the only one that's kind of screwed in this analogy, because everyone, because she gets $1 and then immediately gives it back to me. So now all of you have given me back my money. All of you have gone through the process of giving me $1. So that qualifies you all to leave. So you all get up and you start moving together. Now, notice that you are rigidly held in place. You know me, I don't like for people to be standing up when they're in my classroom. So you guys are all in your place. It's a pattern that I always repeat. Now that you're able to stand up, can you move around a little bit? If Elaine wants to talk to Sammy over there, can she? Yes, she'll have to carry Robert and Ryan closer to her, and maybe Sammy will bring AC and Malachi, but you can talk. The way it is right now, geographically, they're too far away. So you guys all start flowing, get it? Flowing toward the restroom. Of course, this is going to be an awkward situation in the restroom because all for one, one for all. So I recommend, folks, that you do what is common to do in a situation like this. You turn on the faucet so that all you're hearing is faucet water going, and then you do what you must do in order to then go on. So, no, can't cut the rope. So you guys are flowing down the hallway, flow, flow, flow. You see this person coming from the office. They go past you toward my room. Pretty soon you see me coming up. And guys, there should not be any writing. You should be listening to my analogy. So I come up with a sheet of paper, a colored sheet of paper, saying that Maddie's guidance counselor needs her in the counseling office. So I take out from my back pocket these enormous shears, and I cut the rope where she is connected to Freddie, and I cut the rope where she's connected to Zach, and I let her go free. And then I reconnect Zach and Freddie together. Okay? So Maddie's able to go free. The rest of you will continue flowing down the hallway. Okay, you visit the third floor, you come down, always remembering nobody can get too far ahead, no one can get too far behind, because all for one, one for all. So we get to the bus loop, and there, once again, you see me standing by the door. Elaine, because it's 7th period, she's tired of school, comes up to me and says, Mr. Marino, can I leave now? I go, sure, it'll cost you $1. She goes, I don't have any money still. I feel sorry for her. I give her the $18 that I gave her last time, and I got it back, thinking I'm going to keep it, all my $18 back eventually as well. I cut her loose after she gives me $1, and then the most curious thing happens. She takes a few steps, looks back at Robert. Robert looks at her going, could I have the money as well, please? And then with a chuckle, this beautiful, wondrous socialist becomes a capitalist and takes off running, waving the $18 behind her so that you all can see that she has kept the money that you needed
in order to leave the school. Okay? So Robert looks at me and says, I would like to leave as well. So I give him not $19, but $18, hoping that he will be a good socialist and split it between you guys. And I cut him loose after he gives me $1, and Robert is now gone with my $17. I tried with Ryan knowing my money is gone as well. Now I'm thinking Danielle will be the nice, sweet socialist, and she will spread the wealth. She does not. She leaves with, so little by little, I am now hundreds of dollars. Finally, poor Sierra. I give her $1. She gives me the $1 back, and I look at her and I go, well, you don't have any money to keep, but at least you get to leave. And she smiles and takes off running. Okay, how much is it? How much did it cost me to melt you guys? $19. Why? Because there were 19 of you all. How much is it going to cost me to boil you guys? 19 plus 18 plus 17 plus 16 plus 15, on and on and on and on and on, thus demonstrating that human nature works best with capitalism. Why? Are you born selfless and loving and compassionate and giving? No, let me tell you. If you're lucky, your baby will learn ma and da first. But soon after they learn how to call you ma and da, they will learn their first word, which typically is mine. And they will use mine for years. No, those of you who babysit, you know for a fact that you do not have to teach children to be selfish. They come out of the womb selfish. Within minutes, they come to the understanding that they are God, and they start screaming at you if they don't get fed or they don't get something they want. Okay? It doesn't take you long to realize that man's nature is inherently selfish. So, why is it that we were able to overcome you guys' natural tendency towards selfishness when you all needed to go to the bathroom? Because you were all connected together. You had no other choice. So basically, you can have a socialism, but usually, typically, you have to go against human nature and you have to take away the choice from the human being. And it works in Cuba, and it works in China, and it works in North Korea, and it's not working in Venezuela very well, so they're about ready to fall apart. All right, so that's my delving into political science talk. Let's get back to chemistry. I actually just explained to you this chart. Okay? Where are you now along this chart? You are right here. You're a solid. You're rigidly held in place. You're orderly. I need order. That's why I don't like you guys to stand up. I need order. Okay? When I gave that money to Elaine and she had to spread the money around, now what happened? Where are we in this chart? In this flat area right here. That was the process by which you went from solid to being able to get up and move around a little bit. Okay? When you're solid, you're held in place. When you're a liquid, you're held in place. The difference is flexibility. When you are a solid, you can't move. When you can vibrate a little bit, but you can't move. When you're a liquid, you're still connected to your neighbor, but you can move around. Okay, so what phase, what part of this chart is you guys roaming down the hallways together as a team. Yes. Yeah. You are now a liquid. So this is you being a solid now, you melting, you becoming a liquid. Then what part of the chart was me over there with the big giant shears cutting you loose? Which we call boiling. Okay? Then what is it, you guys flying down the street, happy that you have money? Steam. Okay, now there is an exception to this rule. That exception was Maddie. Okay, is it possible for individual water molecules to gain enough energy while they're a liquid, and they should be a liquid, to gain enough energy and go straight into the gaseous phase without boiling away? What do we call that? Evaporation. So Maddie evaporated. So if you go straight from liquid to gas, and you do not pass melting, then you have evaporated. That's right. All right, so what would happen? So you guys are running around, you're right here. So what would happen if once you realize, there's nobody out here. There's only adults, and the adults all want me to work now. I liked it better when I was in school. So it's very likely that the office could very well call me and say, Mr. Marino, your students are standing outside the bus loop door. Can you go and deal with them? So I go over there and go, what's going on? And Elaine's looking at me like, can I come back now? What will I ask of Elaine? Where's my money back? I want my money back. So what is the process by which you go from gas and you start turning back into liquid called? Okay, if you're going in this direction, it's called boiling. But if you're going back down, it's called condensing. So I tie you all back together, you start roaming, and you realize there's nobody else in the hallway. This is quite boring. Let's go back to the classroom and let's continue learning. So if this was called melting, what is this called? Freezing. And once you get back in this room, I go, guys, I can't stand for you guys to be just roaming around. You're gonna have to give me back my money. And then what do? You go and you sit in your pattern, and that's called solid. All right? So that is a heating curve. What does the temperature stop when solid melts? Okay, what happened to the money? In order for you guys to, what did she have to do with the money in order for all of you? Right. So whenever temperature doesn't change, that's when basically the energy is being converted to potential energy. Energy is still moving. Energy always has to move. So because she was spreading the money around amongst you guys, then you were undergoing a phase change. Whenever a phase change occurs, it's going to appear as if no temperature is changing. So all the energy is going to flow from the Elaines to the Sierras until everyone has the same energy. Why does the temperature stop when liquid boils? Because in this case, the energy that I gave Elaine, what is Elaine going to do? Take it away. She's going to run away with it. She's going to run away with it, taking that energy away. What is the most interesting feature of water? Its density is greater as a liquid than it is as a solid. And as we've talked about it before, that is really, really strange. When it comes together, it will form these six-sided crystals. What's the real interesting thing about these six-sided crystals? There's a hole in the middle. So they take up more space. So when they melt, then they all come together like this. So that is liquid taking up less space. Solid is where they're taking up more space. That is really, really strange. No other substance that I know of can do that. Why is the water-ice density difference so important? It allows ice to float on water, causes rocks to be broken down. No, 4 more questions. Then we're stopping. Are phase changes chemical or physical changes? Physical, yeah. All right, is just because you guys are sliding past each other instead of rigidly held in place, does that mean you've changed? What is actually being separated during a phase change? The weak bonds holding the molecules together. The bonds holding the molecules together. These things right here, watch. Boop, beep, boop, beep, boop, beep. If a phase change was chemical, what would be breaking? I would have to dig my nail into this little model and pull away the hydrogen. Now we've got a chemical change because it's no longer water anymore. I've changed water. The forces that hold atoms together are called intramolecular bonds. Intramolecular bonds. And I'll explain that to you more when we meet again on Friday for a lecture.